We will be looking at question 16, June 2023 paper. This question is on lattice enthalpy. Lattice enthalpies can be determined using the Born-Haber cycle. The table below shows you the energy changes taking place. Got electron affinity. You've got two ionization energies of barium, first and second. And we're going to be using this data to construct our cycle. It says the diagram below shows the incomplete Born-Haber cycle. This is quite a typical standard question. It's from last year as well, where they get you to fill in the blanks. Now, you see, first of all, let's start off with the definition. What is meant by the term lattice enthalpy? Lattice enthalpy is where 1 mole of an ionic compound, 1 mole of a ionic compound is formed from its gaseous ions. And we put in our gaseous ions there. And that's a 2 there. You see, on the left-hand side, this over here represents the enthalpy change of formation, delta HF, of the ionic compound. Enthalpy change of formation is when 1 mole of a substance is formed from its elements in their standard state. Iodine is a solid at room temperature and pressure. Now, it's asking you to complete it. So you see what we've got here is we're trying to get these elements in their standard state to these gaseous ions. We're trying to get from there to there. So the state symbols and the charges and the formula, you have to pay careful attention to. What we'll do first, we will atomize the barium. So we write down the same thing again, but this time the state symbol is gaseous. And you see from here to here, the iodine has been atomized here. That's already been filled in. So we've atomized the barium, and the 2I gaseous stays the same. We'll do the first ionization energy of barium. You got that 1 electron there. And then you got the second ionization energy. And we've completed our cycle. Just having a look at the mark scheme. That is fine. Yep. So, just to make it clear to you, this change here is the atomization, let's call it AT, for iodine. The next change is going to be the atomization of barium. This is the ionization energy, the first ionization energy of barium, and then we've got the second ionization energy, barium. Here you've got the first electron affinity of iodine, and there's only 1 electron affinity. And here we are, we've completed our cycle, our Born-Haber cycle. Now the next question is asking us, calculate the lattice enthalpy of barium iodide. You see, we're going to use the cycle and we're going to use all these values. Now, all of these values are per mole, So wherever we're dealing with 2 moles, we need to multiply these values by 2. So can you see 2 moles of gaseous ions have formed here? Let's highlight these. So 2 moles of gaseous ions have formed here. And we've got 2 moles of gaseous ions formed here. So it's really the iodine that we're going to need to multiply by 2. So what we've got, iodine times 2, atomization of iodine times 2. Now, we're using Hess's law again. We're trying to work out the lattice enthalpy, the enthalpy change of lattice energy. Now, from there to there, we don't know what this is. So we're going to have to go from this platform to this platform using the alternative route. And we're going to go like this. And as we've discussed before, the hack, so to speak, for this is that the lattice enthalpy is equal to the enthalpy change of formation minus everything else. Lattice enthalpy is equal to enthalpy change of formation minus everything else. Can you see that you're going against this arrow? You're going against this arrow, you're going against this arrow, against, and you are going with this arrow. So it supports the formula below, and just plug in those values. Enthalpy change of formation. Minus 602 minus, let's open the bracket, everything else. So the minus 296 times 2 plus 503 plus 965 plus 107 times 2 plus 180. I'm working this out. That answer gives you minus 1872 kilojoules per mole, which is your working out here. The next question, this is actually though we're looking at an A2 question, this is a year 1 type question. This is on the first and second ionization energy of magnesium. And you can see here, it's asking you to compare the first ionization energy of magnesium versus strontium. And then explain why the second, so we're trying to compare this versus this, and then explaining why the second ionization energy of strontium is greater than the first. Why is there this difference here? To explain this, let's look at the first point. The first ionization energy of magnesium. The reason for this is that magnesium has a greater atomic radius. Whenever you're dealing with ionization energy, there's three factors. There's distance, shielding, and nuclear charge. Distance, we refer to this as atomic radius. You got your shielding, the shielding of the inner field electron shells. You got the nuclear charge, which is referring to the number of protons. And you want to relate this to the nuclear attraction. So for magnesium, it has a greater atomic radius. It's going to have a greater or more shielding, more shielding. Now, even though the nuclear charge increases, the increased nuclear charge effect is outweighed by the first two. So whether you say the first point or the second point, any one of those two gets you the first mark. Now, you then want to relate this to the nuclear attraction. The nuclear attraction, magnesium, has a greater nuclear attraction. Nuclear attraction between where? The nucleus and the outer electron that's being removed. One mark there, one mark there. Now the second one, what it's asking you is for the second point, is comparing the second ionization energy versus the first one for strontium. Now you see, with strontium, so for the second ionization energy, strontium is removing an electron from a Sr plus ion. So what you're doing, the Sr plus ion has same number of protons attracting less electrons. So the ratio, the proton-electron ratio in strontium plus ion is going to be greater than the atom. And that's why it's going to have a greater nuclear attraction. So the number of protons in strontium is 38. And the number of electrons is 1 less. So this is going to be greater than the atom. And that's why this gives you a greater nuclear attraction. And these are your 4 marks. See you next time.